Okay, so now we actually have something that works a little bit. We can actually generate assembly now and compile it to executables. So let's do some examples. Right now we can only use function calls like this and put strings and numbers in them. Like we can print strings and ints. We can also read strings and integers, but we cannot really use variables yet. I still have to implement that. But we have comparisons, we have while loops. So I mean, let's try to see some examples. So for example, this one we read the number from standard input, and if it's smaller or equal than 4, we print a message, and otherwise we show hello world. So if we try to run this thing, you can see that we actually get the result, right? It was I input 6 and it showed hello world because it was larger than 4, and this is how the assembly looks like, right? So yeah, I spent quite a lot of time to add these comments, and I think they're pretty useless in the generated code. Maybe they are useful when I iterate over the how to implement stuff, but that's when I do it manually. So yeah. Then yeah, let's try to add something more interesting. For example, a while loop, and let's say while we can do a while true, but that would be kind of pointless because it's gonna kill it. But let's try to do something while we read something that's less than 10. We print a message. So now if we, I mean, yeah, sure, let's just do it like this because it's easier. It recompiles everything. So the first one will be still for the for comparison. So if we put 10, it's gonna say hello world. But then if we do 5, 4, 3, 1, 6, 7, there are no negative numbers though, so that's something. And yeah, we input 10 and it exits. That's pretty nice. Oh yeah, and see, like it also called this function. But these are kind of all the functionalities right now. Um, we don't have arithmetical operations yet, although no, they are in the AST. So if we take a look at what is currently in like implemented, I guess we can look at emit expression. I just have to find it. Emit expr. And yeah, I guess what we did was convert from the AST expression into TAC instruction, tree address code, and then we convert each tree address code instruction into an assembly instruction. I thought it's gonna be a lot easier, but I think I haven't really got the best tree address code set of instruction. I think the instruction set was pretty lame, and yeah, I mean the conversion was still pretty a lot of code. What I meant to say, and that's mainly because all the values in cool are objects. So you have to take an int, for example, create the prototype object, and then assign the int value to the attribute of that int object. So that's why it's a bit trickier. Like yeah. So yeah, let's say the instructions that we currently have. So the labels and the jumps. These are mainly for conditional loops. Then we have the assign, which currently doesn't really do anything because we don't really have variables. But I might be wrong. I'm pretty sure because let's try to do let x. Okay, let's do it outside. Let x equal to 0 in. But yeah, it's not really. Actually, I think it should work. So x is equal to in int. Let's do out int. Let's do something like a new line then. Maybe something like this. Let's see if it actually works. So yeah, we don't. Well, I forgot to add the the block for the, because you cannot have more expressions. I think this is how the syntax should look like. I'm not sure if it should be indented like this. It makes sense like this though. Yeah, let's see. Yeah, and tokenizer is a bit ugly, but yeah. Okay, so yeah, it doesn't work. It's yeah, we'll have to see. But like this is something that I have in plan, basically, to use also variables and also attributes like this, so be able to use them. So that would be really cool to have. I mean, I'm not really trying to use the name of the language. Okay, so um, assign values, these are not really used, as I said, because yeah, I mean, maybe they are like in the while loops and stuff. Yeah, for the actually for the if statements, because each branch will return something, so it has to do an assign. But yeah, then the dispatch call, which is just a function call like this, which also works if you do self dot. Yeah, I think it should, and I think it should also work if you do something like this. Although, I mean, I'm not sure why it didn't print the stuff. Hmm. I don't even think it's possible to. Yeah, I mean, maybe something. Oh, because yeah, I think I did on A, so A doesn't exist, but it didn't show the error for some reason. Yeah, because if you have syntactic or semantic errors, it should show you the error, right? So yeah, okay, and after that I also implemented the comparisons. One that's more interesting is gonna be equal, because like less than and less than equal will work only on integers, but equal should work on any kind of type. So we have to implement basically memcopy in assembly, or I meant memcompare in assembly. Then we have not. This one is for the while loop. Identifiers, I guess these are just creating new identifiers, the temporary ones, not the ones that we actually want. Like to use those, we might need to change the logic in the code. Like we don't really have new instructions to add for that. We just have to change how we find the variables, because right now we only look on the stack for variables, and those are the local ones, like temporary variables. But we also have to look on the in the object attributes and still on the stack for the arguments of the function, but that's more like, I guess, uh, right now we look only on the current stack. We have to look on the stack of the arguments, right? Like above our RSP. But yeah, I guess these are all the instructions that we have right now. And yeah, probably in the next part, the compiler will be complete, I think, with everything. And after that, we might even try to do more interesting stuff. Like I also added this extern keyword, which lets you define, I guess, the objects like this in the code, so we don't have to hard code anything in the compiler. Like we can just define the CL file like this with all the functions that we want, and we might try to, I don't know, like maybe add in IO something like create window or draw stuff on the screen. So that would be really interesting to have graphics in this. I mean, you know, it's I think it's such a like crap language that it would be actually fun to do a game in it. I don't know, because it literally doesn't have like anything. It only has integers, strings, booleans, and this IO for input and output with strings. So yeah, we might have to implement an array, like a linked list, and I don't know, maybe do something like not really game of life. That I think that would be too hard. But rule 110, I guess that's doable in this one if we do something with yeah, and I guess even game of life would be interesting if we can actually do graphics, but I mean I doubt that that's possible. But yeah, we'll see. So yeah, I guess this is how a cool programmer looks right now that we can compile. So yeah, in the next one, I guess I'll let you see the full implementation and see you in the next one. Okay, so for the first part, I just realized that we might actually need the context that we built in the semantic check. However, yeah, it's not really that great to use the one that we have. We have to use the one from the description, like from the operational semantics in the book. So I just created a structure just like that. And I mean, the code is gonna be like this part is gonna be just me copy pasting the code from when we did semantic check. So I don't think it's that interesting, but at least I can explain the thought process. So my idea is to have the parent mapping. So that's the first thing we have to do. The parent mapping will be just like the context itself. So it's gonna be the a list of I don't know how to call them, like a list of structures, and each structure is gonna be the name of the class and a pointer to itself. So like a structure of itself. So it's gonna be like if you look at the AST, you are gonna see something like, I mean, not really the AST, but if you look at the inheritance of a cool program, it's gonna be something like a tree, right? You are gonna have the object at the root, and then it's gonna go outwards towards all the classes. But what we actually want to have is something like the reverse. So we have a list of all the leaves, and we want to have a pointer from the current class to its parent. So this is the structure, the parent mapping item. It's gonna be the name and the pointer to another parent mapping item. And we are gonna have a list with all the leaves. So basically it's the reverse of a tree if you think about it. I have no idea if it has a name, that data structure, but it's the easiest way to keep track of the parents of classes. And yeah, I mean, after that, after the parent mapping, we also need the, I guess it's called object mapping. So, or like class mapping. In the book, it's class mapping, yeah. But class mapping is basically for each class we need a list of attributes, and that list also includes the attributes from the parent. So yeah, like you also take the attributes from the parent. So if you have class A, which has, let's say, attribute A, then you have class B, which inherits from A. Class B also is gonna have the A attribute. So that's the idea. And yeah, I guess now you'll see that I just pretty much just copy pasted the code from previous um, episodes with from the semantic checks. But yeah, so I was at the class mapping. So the class mapping is pretty simple. It's gonna be just a list, right? And each item in the list, because we cannot really use hash maps. I mean, it's too annoying to be honest to use hash maps in C. So we just make a list, and each list is gonna be a key value pair, basically. So we are gonna have the first, like the key is gonna be the name of the class, and the value is gonna be a list of the attributes. And to make things really simple, the the attributes are gonna be pointers to the nodes in the AST. So we keep something like that, right? We know each attribute, like the name of each attribute, and we know what part of the AST it represents. So later on, when we are gonna need, let's say, variable v or whatever variable value, we can look in the class mapping, take the attribute value, we find it, take that key value pair, and we can point into the AST and see, well, this is the expression of value, right? Something like that. I guess that's my idea. I'm not sure. Probably it's gonna work. For sure it's gonna work. Like we can work around it if it doesn't work, but I think it's enough information to be able to do assembly. But yeah, that's my idea. So keep a pointer to the AST itself, to the expression from the AST for each thing. And then for the last thing, for the implementations mapping, we do something similar, but this time we keep as the key, like the key is gonna be two things. It's gonna be the class and the function. So something like that instead of just the class. So we are gonna have again a list, and the key is gonna be the class and the function name, and the value is gonna be, you guessed it, a pointer to the method node from the AST. So pretty simple. When we are gonna need, let's say, but I mean it doesn't really matter because yeah, like to be honest, I think we just need the names. We don't really need the implementation because we are gonna generate the implementation as tree address code, then as assembly, and we are gonna use labels with the names. So when you want to jump to running a function, you jump to that label. So like, I don't think we really need the implementations. But yeah, we'll see. I really think that it's a good idea to implement this though. So that's why I actually did it. But I mean, it's exactly the same as building the environment types. So yeah, I guess I'll just keep through it and probably, yeah, hopefully in the next part I'll be just doing assembly, right? I mean, yeah, I mean the point of the entire episode is to get to assembly basically. So yeah, hopefully I'll be able to do that. So see you there. Okay, so for the second day, the plan didn't seem as complicated as it actually was. So my idea is to use Phasm for the assembly. For the other compiler that I made for Brainfuck, I used Nasm, but yeah, I thought it might be simpler in Flat Assembly. Yeah, to be honest, I haven't used it before, so it was more like, okay, let's try it out, let's see how it goes. And yeah, to be honest, it was extremely painful. I have no idea why it was so difficult to get it to work. Like, it took me almost 2 hours to just be able to define variables. So, I mean, I guess I'll just, explain what I wanted to get, then skip to where I actually got something going. Although it's not that much, like we don't have an executable yet. Like that's the idea. And yeah, so my idea for how the assembler or like the assembly would look like by looking at other projects and just copying other people is yeah. So I saw that usually people will have a name table for the classes, and in this name table we keep, as you might have guessed, the names of the classes from our cool file. Then what we need is the so-called object table, and this object table will have two like references to two things, to the init of a class, and that's, for example, for strings you, or like for ints, let's say for ints you would put 0 in the attribute, so that's the thing. And for, let's say, a more complex class, you would put void or whatever, you initialize the attributes. That's mainly what init should do, initialize the attributes. um, that's why we also keep that object mapping. So the object mapping keeps track of the init expressions for all the attributes. So the init would just execute those instructions. So we have the init of a class, and the other thing that we need is, I guess, the prototype object of a class, and this is like a blueprint. And how the program will work is, when we create a new instance of a class, we are gonna copy this prototype object, um, like just copy it with probably object.copy, and yeah, then the prototype object will have a dispatch table with all the methods that are available in that object and the list of attributes. So that's how we are gonna keep it, like the data structures. And yeah, we have to figure out how to handle stuff on the fly, but I think this structure should probably work. Like it, to be honest, it sounds good, but you know how it is. It's probably not gonna work somewhere like in the middle of it. It's gonna fail somehow. So yeah, at this point I was just doing like the boilerplate of making the executable be able to get a flag for running the assembler. So like a dash 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 asm for running the assembler. And yeah, I was just checking that everything works. So yeah, I mean, the idea was, because I have these examples which use MIPS, or yeah, it's like another type of assembly, but I want to be able to generate the native executables, so you don't need any emulator or something. You just um, compile it to assembly and then use Phasm to generate the ELF64 executable. So that's the idea. And yeah, at this point I was just looking through the documentation and stuff, trying to understand how to write a simple hello world. So yeah, and after like a lot of struggling, I actually figured out how to do the hello world in Phasm. I mean, obviously it's pretty similar to other assemblies, but yeah, just using these segments instead of sections. And maybe the other thing was how we initialize the data. That was, and how we initialize the data. That was a big problem, because here you can see that each label has is defined like a word with three, a word with five, a word with or like a word is more like bytes with the string and so on. So you have this structure like initialization. And in Phasm, the only way I know how to initialize stuff is to use db and then put like all the bytes, like all at once. So I didn't really know how to, let's say, generate the right data structure. But again, like it took me, I guess, what, almost 1 hour and a half from this point to figure out how to, I guess, just have this type of structure like initialization. So I needed the first field in a string constant, which is the type. That's what I think it is. It's the type of constant, like int, string, or boolean. Then the next thing would be the value itself. But for strings, we have the string length, which is a keyword. I mean, you can use, I don't know what to use. I try to use keyword for it. And then you have some bytes. So yeah, here I was just doing the header, copy pasting it from the hello world example. But yeah, it's gonna be a bit more interesting when I get to the actual constants. Well, I mean, it's not really gonna be interesting because I wasted a lot of time there, but that was the main idea. How can I initialize the the structure? Because it looks more like a structure than just an array of bytes. So yeah, and I mean, I tried a lot of ways to do it, like, yeah, combining them, but I didn't realize that you can use new lines to separate the field, so that was how to do it. And afterwards, the next thing where I wasted a lot of time was being able to use already declared labels inside of my labels. So yeah, and the idea there, like, yeah, I couldn't figure out how to take one existing label and use it in my structure. And yeah, as I said, the actual way to do it is to use new lines to separate each field. So for example, in this one, I defined my data, which holds a DQ, which is like double keyword, like 8 bytes. And then I put there the name of the label, which is some data, and that's a pointer to some data. And on the next line, I have db hello world, and then new line. 0xa is character for new line. And some data is just an int with a value of 2. And my issue when I was trying to do the printf, which is the first block in start, is one is the syscall, the next one is standard output. Then I have my data plus 8, which is the memory address of the string of hello world, and that's the first argument. And it's plus 8 because we have dq as the first field in the structure, so it's 8 bytes. Then in RDX we have to put the length, I guess, for write, how many bytes to write. And my mistake was I was trying to put the value from my data plus 0, like the first field, and was taking the value, but the first I didn't realize that that value is actually an address. So it was really weird. It wasn't compiling or I guess it was compiling, but it was not giving the right value. And yeah, basically that's why I wasted so much time. And then I realized that, well, I can just dereference it again, like do RDX, pointer RDX, like on line, it's line 8 there. No, I mean it's line 21 minus 8. Whatever, you get the idea. It's below, um, it's above the syscall. So yeah, we dereference it once more, and now we get the actual value of my data. So yeah, and I mean we can also just move it, but yeah, some data was actually the pointer to data, and when we run it, it was showing just hello, or just the part that was actually needed. And yeah, at this point, what I was trying to do was to add comments in the assembly, just to know what each instruction does. And here again, I wasted a lot of time trying to get it really fancy with like variadics. And yeah, I mean, it wasn't really that like I was getting stuck. It was more like trial and error until I managed to get it to work. And to be honest, I don't know how to make this thing to be a bit more pretty. It's like the assembler emit function will start to get really ugly. Like it will have an argument for the comment because I decided to put as an extra argument the comment. Then it will have an argument for the alignment, like for the padding of the start. And yeah, basically that's how it's gonna turn out to be. So some like yeah, this one was pretty interesting. How to get like the padding from the end of the line up until the start of the comment. And the idea is to use snprintf. And when you use snprintf with the first argument as null, it actually tells you how many bytes you need to allocate to be able to use snprintf. There I think it's wrong. I think I should use snprintf. I used the other one. But I mean, I'll change it later. But yeah, that's like a really cool thing that if you use snprintf with null, then you actually get the amount of bytes you need to allocate to be able to run it. And like that's, I mean, it's really cool because yeah, I mean, obviously it's really cool for C. Uh, yeah, I forgot when I learned that, but probably it was the hard way, so that's why I'm uh, trying to make you remember it because it's gonna be cool to know it in future C projects when you have to work with strings and it's gonna be ugly. But yeah, here I had that comment, but I guess because of I guess how the VA list works is that it doesn't really have an ending to it. So when I'm doing that snprintf, it's not gonna work with the variadic arguments. And I guess the actual fix for that is to use vsnprintf, which I had no idea it's a function. I just saw that vfprintf, and I thought, well, can it be possible to have vsnprintf? Like, is that a function? And it actually is. So I changed to using that, and well, I figured out that actually these functions which start with v actually consume the VA list. So we have to do VA start again and VA end and have just the smprintf in a block. It calculates the size, and then we do vprintf in the other block. So this made it almost work. We forgot to add the alignment, and yeah, there we go. And yeah, now we actually have aligned comments, which I mean it literally has nothing to do with the compiler, but it was like a really cool tangent to go about. And yeah, like we have aligned comments, and that's completely useless to be honest. But I mean it's cool, right? Like if you want to have aligned comments or align something for some reason, you can literally just go in this code, copy paste it, and I mean you have it for later things, right? Like it's still a good thing to have. I mean, probably. Although, yeah, like to be honest, yeah, I see no use for it. But no, just that the comments will be aligned and your eyes won't hurt when you have to check the comments. I guess that's a positive about it. So yeah, and Now what I decided to do was to create the class name table. So that's the first step. And I guess, yeah, it took me almost 2 hours to get to doing the first step of the compiler, and that's the class name table. So the class name table, as I said, we have to go through all the class names in the context. So we just gonna have to iterate them, right? And how I changed this code actually was, instead of generating all the constants in the beginning, I actually change I'll actually change the logic to generate the class table, and when we encounter a new string constant, we generate a constant for it. So it's like a lazy approach, I guess you can think about it like that. So we find the constant that we need to use, and because of that we add it to a list of constants, and at the end of the compiler, um, like after we are done with everything, we are gonna emit all the constants. So yeah, that's my idea of how to do it. So for the table, we just need to create a constant when we encounter like a class name. It's always gonna be a new one, so it doesn't really matter. So we generate, and yeah, how I change the um, constant value for string is to actually also keep a reference to the length label, because yeah, I mean it's easier to just keep a reference to the length label, like the constant int with the length of the string, So yeah, and I mean yeah, so we encounter a new class, we generate a new string, and I guess that's everything for that part. So yeah, and I guess for the next parts we need to generate the object table, and then the dispatch, and also the init. So I'm gonna try to make it so that we can get to a hello world as quick as possible, I guess. And that means I also have to implement all the assembly for IO and all of that stuff, which it needs to be implemented in assembly, and yeah, probably that's gonna suck, but it is what it is. So I guess that was everything for getting the class name table, and then all the constants. So yeah, I guess that's a pretty good start. So yeah, after getting a bit more used to the FASM assembly, I decided that for the second day I can try to finish the, let's call it, entire skeleton of the source code. And that just means that I want to finish all that I proposed here in that to-do statement from the main.c file. Basically, we did the name table, that's complete, I marked that. And for this part, which took a lot less time than the first half, I decided to work on the object table. And as I said in the beginning, that's just references to prototypes and inits. And yeah, basically for the inits, I'm just gonna put the blank label, nothing interesting there. It's gonna be just the names. And for prototypes, I want to have the, let's say, dispatch table name, and all the methods, and also initialize the attributes with zeros, because yeah, for now it's enough to just do zeros, and we'll work on the complex stuff later. So yeah, let's see. So the first thing was just checking how it's actually implemented, or at least in Force PIM or MIPS, whatever it's called. And yeah, I put there two functions that I have to implement, making the object prototypes. And as I said, that's um, like the attributes and the pointer to the dispatch table for that method. So yeah, at this point, I thought, well, it's gonna be nice if I have a separate function that I call by using the index, because we are also gonna require to use different labels that depend on the index. So yeah, but here at this point I was just checking how the assembly code should look like and what each field from this example means, right? So I figured out that the first one was the index in the name tables. The second one seemed like the size or something like that, although in my implementation, to be fair, I'll be using the number of attributes because I have no idea why you would need number of attributes plus 2. Like, it's just number of attributes plus 2 everywhere. So I'm just gonna put the number of attributes, and if we need to use plus 2, it's just plus 2. So yeah, that would be easy. So yeah, here I think I created another function that prints a single prototype, so we can iterate over all the classes and print the prototype for each class. And yeah, it's gonna use the index because the index, as I already said a couple of times, is the index in the name tables, right? So yeah, I also wanted to improve a bit the comments. So how it was really painful to get them to be really aligned, and yeah, like now I can actually make them a bit useful. For example, in the name table, there it's like you can't understand anything from the name table. It's just string constants. So how about using the class name in the comments so you know each string constant what class name means, and that way we can also double check that we did everything right. And it's also a good opportunity to finally make the when we create new labels to make them like unique. So if we have duplicates we skip them, but yeah, let's see what was next on my list here. So I guess just doing the prototypes, for some reason taking a lot for the prototypes, although it was just I mean it was already done. I have no idea why I was still wasting time on that. I guess something else I have to do is to also print the attributes, so maybe that's why it was, yeah. But see, I put the index in the name table, and here I guess I'm not sure if at this point I thought that maybe it's a good idea to have better comments for the name class name table. But yeah, here like that looks like the size, right? That number. Yeah, I mean anyway, I guess that's why I was a bit confused, and also something that was really confusing, but I figured it out quite fast, was the attributes, like the initialization. So we can initialize all the attributes with zeros, right? But I was thinking, what if an attribute has an expression, like an initialization expression? You have to do some assembly that calculates that thing, right? And yeah, that was really confusing because here I was searching for an example that had more complex initialization, but I was like, well, there's literally no example with that, and yeah, that was strange. So I'm not sure at which, like, to pinpoint the moment I figured it out, but um, I realized that we have the init label, and init is actually just that. It does the assembly for the expressions for the attributes. So if you have a more complex initialization for an attribute, we are gonna calculate that in the init uh, of the method of the class. Sorry. So yeah, basically that's what init is for. So I literally had there was no point in worrying about this thing because we can just put zeros, and I guess for constant values we are going to initialize with the constant value. But for now, let's leave it as zero, just to get just get over this step and move to the next one, just to stop pondering on this one. I guess usually it's better if you get stuck, just try to make it work, get to the next thing, and then come back to the thing that made you stuck. I think that's a good approach to it. Like, just do something hacky and then come back to it. So yeah, here I was thinking how to handle the complex expressions. But as I told you, the idea is we handle the complex expressions in init. So that's how are we gonna do it. But simple expressions like constant values, we can handle them right there. We can create a new constant using our function, and we are just gonna use that constant. But again, I just stopped at 0, left a to do comment. Hopefully, I mean, just grab the to dos and actually fix it. So yeah, here I also created a small function for generating comments. And yeah, I'm even scared to look at the memory allocations because I'm pretty sure we have like two frees and 400 mallocs. So that's gonna be. I mean, yeah, I'll be honest. I'm not gonna try to make it memory safe. Like, no, no way, it's gonna happen. Although it is possible. I mean, it's not that hard. So yeah, here I put the name of the attributes. So you literally know which attribute each like keyword represents there in our list of attributes. So that's pretty nice. But yeah, let's see, because at some point I'm going to change the to do comment, and that's the moment I realized that well, init. I guess I figured it out that init is actually the one that initializes the attributes when I implemented the init part. But yeah, and for init again, as for the other stuff, I just put a label, nothing else, because here I realized it. But yeah, for the init we are gonna require to write assembly, so I'm not really ready yet to do that. And yeah, let's just leave the bare bones of the assembly, and yeah, figure out how to write actual assembly maybe in the next part or something. So yeah. And here I also implemented that thing that I mentioned, where we look if we already have, let's say, an existing constant with the same values. So if we have, an int twice, then there's no point in generating a new int. The same thing for strings, and yeah. But I mean, it's gonna happen a lot often for ints. So yeah. This is just optimizing for space a little bit, because now instead of having, I think it was 19 before, 19 constants, now we have only 14. Oh, it was 20 constants, and now we have 15. So yeah. And yeah, for the class table, I also put a nicer comment. So now if we look, we have the name of the class next to the string constant, and yeah, just now I was just improving a little bit the comments, because for example in the object table we don't really need comments. They are pretty useless because you literally know what that thing means. But when you don't really know what it means, I said, okay, let's leave the comment, because I think it's better to have it for, if you have numbers, like what does that number mean? So yeah, like if you have numbers or strings or some variables, I think it's better to say what it means. But when you have something as clear as main prot object, then I mean that's the prototype object. Everyone knows. Okay, and let's see what was next. So I guess the dispatch table. And for dispatch table, here I overcomplicated a little bit. So when I built the implementations mapping, I only looked at like a depth of 1, so only at the current class. And I didn't really put into the implementation mapping, like let's say methods from the parents, methods that our class inherits from the parents. I only put the current methods, and I think it would have been better from the start, from the beginning. Although I did that in the beginning. I did it like the current class looks at its parents, and it puts into the implementation mapping, it puts all the functions, all the methods that are present in the inheritance chain. But then I changed it to not do that for some reason. I don't know. I was just saying, well, when we print the implementation mappings, it's too huge and it's annoying. And I thought, well, maybe we can recompute it in the code generation. But to be honest, recomputing it here, I mean, it's we get the same problem basically. It's still annoying regardless. So I would rather do it in the semantic check because I think it fits better there than here in the assembly generation. So yeah, instead I just moved to the semantic.c file, and here I was gonna just add a while loop outside of this thing that just iterates over the current context dot parent, so it goes up the inheritance chain. And yeah, let's see how I did. I mean, I did this one before, to be honest, but I took the parent name. I also had a method name and the current class's name. So I had all of these three parameters that basically define a method. So we have the current class, we have the parent name, which is the class where the method is defined. So yeah, sure, it can happen that the parent name is equal to the class name, and that means that our current method is defined in the current class. So um, if we want to make a better, like a prettier print, we can print only that, like only the methods that are defined in the current class, and that would make the printing a little bit smaller. And maybe that would have, if I realized that sooner, maybe I wouldn't have had to implement this twice. But yeah, I mean, it is what it is. And yeah, I mean, I actually just managed to, yeah, also, if you, like, you kind of have to check that the method is not already defined, because otherwise you would define it for every class in the inheritance chain, and you don't really want that. You want to see it once, and you want to see it only for the most like up-to-date implementation, like for the most overwritten one. I have no idea how you would say it. I'm not an OP. I mean, I'm programming in C, like a compiler for an OP language. That's and to be honest, don't really use OP. Yeah, it's. I mean, literally, if you implement this kind of compiler for an OP language, you kind of um, understand how OP is just in like imperative programming, right? Like we, like you can see here in our assembly from the compiler, we just put all the classes into a list of, um, well, I guess we put all the methods into a list of functions. So you literally just see how the OP goes away on the level of the executable. It's pretty much just imperative programming at this point. So we just have all the methods, all the attributes are like global variables, and when you initialize a new object, you just copy it into the memory. Like you copy all its attributes globally. You copy, like the methods are not gonna be copied because they are just assembling the code, but it literally just turns into imperative programming. So it's pretty interesting. Yeah, I mean, I guess OOP is just syntactic sugar if you think about it, but yeah. But yeah, I really think that it's a nice idea to implement a compiler for an OOP language that you really learn a lot. And it was pretty interesting to get to this stage where now we have the assembly, like the outline of the assembly, I guess. Like we defined all the methods, all the inits. We just have to write the code for the init. But we also have to write the code for the methods. But yeah, like look at this point how quickly I was able to just make the outline for the methods. It was just, I mean, obviously it was easy because I only put the label. I didn't really add the body yet. But see, here is what I said earlier, that we check if the parent name is equal to the class name, and when that happens, that's when we actually define the method, because that's the only place where it matters, right? It's the original definition of that method. Yeah, I guess that's how you can call it, where it was the latest version of it. So yeah, now I was just looking through the to-dos, and probably will go through the to-dos for implementing the code in the next part. So yeah. Okay, so the plan for this part is to get some assembly going, right? So what I changed about the previous parts was introducing that external keyword, and now we can have an assembly file because it's easier to write the assembly file itself, not in C strings. So yeah, instead of doing printfs, we can have a separate file with the data or like the instructions. And the first step was to just define some of the constants, and after that, I guess I'll just go through the main file and copy from that implementation. I also changed everything to keywords because it's gonna be less of a pain to just have everything aligned by 8, so that should be easier. And yeah, I just check that everything is a keyword, and yeah, I mean, instead of using 4 like indices of 4, we'll be using 8 because it's 64 bytes. Okay, 64 bits I meant. And yeah, now I'm just checking the previous assembly code that it still works, and yeah, I guess put some different type of comments for some reason. But yeah, I just want to keep it as true as possible to this, let's say, base implementation. I guess this one is, I don't know, from like the author or something. I have no idea, to be honest. I just stole it. Um, but yeah, so now I was just copying the methods for the base classes, which I define them as external. Like I use the external keyword next to the definition, and I guess that's like an extra feature I want to have in the language so we can easily extend it. Like it's gonna be interesting. We can write assembly code for that, and yeah. Um, yeah, at this point I wanted to check how I did some of the assembly in my previous project with a compiler, but that was really simple. It was for BrainFuck, so we had like what 20 lines of assembly, like different lines, right? Because I mean the assembly itself was pretty large, but we had 20 different instructions, so pretty simple. But yeah, I decided to just copy all the headers, and we'll go like if we get an error, we try to fix it by implementing the assembly for it, something like that. We are gonna get a lot of segmentation faults, So when we actually fail, we do that. Now I was thinking to use the syscall um, convention of using the registers as arguments, but to be honest, I changed it back to using the stack because it's gonna be easier to keep track of the like generic way of doing it, like if we use the stack. So that should be simpler. But yeah, just like for the next couple of minutes, I guess I will just be copying stuff, so I'll skip that. And after I got all the functions down, I decided to try to implement outString first. And that's just so we can get a hello world message done, so we can actually see something. And like because it's gonna be easier to debug if we have a printing. We are gonna do printf debugging. And something that's I don't know if it's but I think it's pretty painful. I have no idea how to add debug symbols to the executable. And yeah, I mean, we can still debug it with GDB. I found a way, but yeah, I'm not sure how that's possible. Yeah, I mean, strange, but I thought that Phasm itself has something for doing that, but maybe I'm wrong. Maybe the compiler has to generate um, the symbols actually. I mean, GCC does that, to be honest. So yeah, I guess it sucks, but I mean, it is what it is. It's still manageable. Like you can still use GDB to debug it. But yeah, here I was just trying to learn assembly actually because I haven't coded in assembly in a while and I totally forgot how to use it. And yeah, this push instruction is kind of new for me. I haven't used it before. Usually, what I did was know, do a stack pointer minus 4 or minus 8, whatever the size of the data is, then copy it on that address, and yeah, I guess that's everything. But I guess push makes it a bit easier because you don't have to keep track of allocating the memory on stack, and then at the end you have to do pop. So it's easier. I mean, uh, the other way of doing it was adding 8 or whatever I subtracted in the first place. So I mean, it's still not difficult, but push and pop makes it more obvious what you are trying to do. Like there we are storing the self variable on the stack. So yeah, as I said, we are gonna use the stack as the arguments, and RAX will be the register where we are gonna keep self. So we are gonna use Rux, I guess, just for self or something, and I'll be using RBX for doing like computations and stuff. I guess, yeah, I mean, having more registers would be really cool, but no, maybe let's try to just, stick to, because if we manage to write code by using like two registers or something like that, it's gonna be easier to make it more generic, I think. So I'm gonna use like RBX, RDI, and something like that just for because they are also part of the syscall parameters. Like I'm gonna use those registers for doing computations. And yeah, basically try to keep array as probably as clean as possible because it's gonna keep self inside of it. But yeah, I mean whatever. So at this point I thought, well, I actually did it. It's the printing is done, but man, I was wrong. Uh, because yeah, I was really confused because of the memory addressing. I guess the FASM, like the assembler itself, makes it a bit easy for you because it's gonna tell you if it's something wrong, like on the level of if you're trying to use a variable, I guess it doesn't really tell you that. I was thinking more like if you try to move from a variable into a register, it tells you, but not really. It moves the address. So yeah, and here I guess this is a really good idea to try. Like if you really get stuck, here I was looking at assembly generated from my source code. Like I was looking at how real assembly looks like, basically. And yeah, I was trying to see, okay, what does RBP and RSP mean, right? Like the return address and the stack pointer. So I'm just storing them for like at the end of the function call, we have to reset the stack pointer to its original thing, whatever. And yeah, the return pointer is used with ret, so it's useful. But yeah, now I'm just trying to improve a bit the assembly code. And yeah, as I said, we were getting some segmentation faults because of how I was using the variables and the memory. And I was trying to use GDB to debug it. And I mean, it actually works. At least if you want to see what happens or where you have the segmentation fault, that's a really good way to find out. Like you just run it in GDB and it will tell you the instruction where you get the segmentation fault. But yeah, like another way to do it if we had symbols was to run it with Valgrind, and that also gives you the like a better description of where it happens. But since our compiler, because I guess the compiler has to generate the symbols, well, we don't generate symbols, so we don't have debug information. So we just have to rely on stepping through the code. But yeah, I guess all that I have to do is to get a better convention on how I write the comments there. Like for example, like axis offset. It's not really clear what it does. So um, I think the best way to do it is by using like a star to represent if it's a pointer. So yeah, in the comment, like say that okay, RBX is now a pointer to this thing. So I mean, make it more like C. So it's easier to keep track of what each instruction does. Because yeah, it was a bit unclear. But the idea for okay, I guess I also can explain what outstring should do, right? So the string class has two attributes. It has an int attribute, which is the length, and that int attribute is basically the length of the string, right? And that attribute has type int, so it's an object. However, the string, it's not really a string type. It's not an object. It's more like the like x.s is not really a reference to a string object. It's a string slice, how you would call it, but this thing doesn't really exist in cool. So even though in the prelude.cl I wrote that s is a string, I mean in my idea, if I say it's external, it means that it's some kind of pointer and it's not meant to be used by the user or something. So probably I'll have to add some checks that you don't use external in your code or something. I mean, it's a bit of a hack, but yeah. And yeah, I mean, after I played a bit more with the memory, I was getting that weird printing, but I still have to figure out why that happens. But yeah, let's continue with the IO class. So I'm in the string class. So it has I said that it has that int attribute and that string slice attribute. So when we access from the memory the int attribute, we actually access the int object. So it's like another level of indirection. So we have to then take that memory address, um, and if we want the actual int value, we have to go into that address, or not really into that address, but like increase the address by the offset of its attribute, of the int attribute. So only then you can get the actual value. So yeah, how this function works, outString, is that we have this, in the beginning we save everything, like save the return address, save the self variable, and then we have to get the first argument, which is on the stack. As I said, I changed it to work with the stack. So the first argument is going to be at RBP plus 16, and I guess, yeah, that's like X, because we saved on the stack the, the return address, and after the return address we have the arguments of the function, and after the arguments we push the self, right? So we have the arguments and then we have self. So the idea is we get the string, and the first thing is to get the str field. So we have to do .s, and if we get the address of the string field, we are gonna get back a pointer to like a literal string value. And I guess that's enough for printing, because we can set the buffer to like the argument of the right syscall to that string slice. So we just move it into RSI, and then for the length thing, it was a bit more tricky, but what I did was uh, kind of similar. Like we get X again, then we get the pointer to the L attribute, which is of type int. It's like an object, but it's still a pointer. So the next thing we have to do is to dereference it. So we do just that on the next line, and now on the next spot we have to get the, but my guess is that that's where I had the bug, because for string I use the pointer, but in this case I used just the literal value. And how the write was working is that it was just printing a lot of trash. So it means that we pass in the wrong size for write. So that's what happens. So at this point I was just trying to GDB the thing and see what value we have, I guess, in RDX at after that instruction call, but I had no idea how to set breakpoints. So and I found the way how to do it on Stack Overflow, obviously, and yeah, you actually have to use start I, and I guess that just goes to the first instruction or something, and then you can use step instruction to go like step. And yeah, here I was just debugging everything, looking at the data, how it looks like, the memory layout and stuff, just to see if we get everything like how we expect it, right? So here I was just trying to see if before we do the syscall, all the variables, I guess all the parameters to the syscall are right. And yeah, I don't know what I was doing in the code actually, because the problem should be with assembly, I guess. Oh, I was trying to do like put some random data in the init, so we can have something to look at instead of just 0 and pointer of 0. But yeah, so changing the alignment so we can see properly, but yeah, I just continue with basically a lot of debugging, and was trying to figure out why the length of the string was not right. But yeah, I mean the string was fine. I just saw that. However, the issue, yeah, should be with the string length, and to be fair, I don't remember what was the issue. Probably, actually, I remember. It was because the int constants and string constants and so on need to have the same format as the prototype object. So that's why they had a lot of extra crap in that in those assembly files. So yeah, that's what I'm gonna change in the end. I'm gonna make them look exactly the same as the prototype object, because if you think about it, the constants are just copies of the prototype objects, but they are instead of being created at runtime, they are created at compile time. So that's the only difference. So yeah, actually that was the problem, the size of the variables. Because I think in the end I actually used the right addressing. Oh, and the other thing that was a bug, I remember it. I was putting the instead of putting the last value in RBX, I was putting it directly in RTX. So yeah, it was like a single character typo that led me to like an hour of debugging. But I mean, it's fine. Um, I still, at least I figured out how to use GDB with this assembly, because like without like symbols, starting it with start I and then doing the step instruction to go through the code. So I mean, it's still like a win. But yeah, as I said, like after a lot of more debugging, I actually managed to find the fix. So here I was just checking that everything was fine, and I think I saw that I had the move RDX pointer RBX, so that was not right, and now I fixed it, and I was like, oh my god. And now if we actually try to compile it and run the source code, we are gonna see the actual thing displaying the hello message. So yeah, that's pretty nice. And the only thing I had to change here was to make that to a 5 to have the same length as the string. Now if we actually run it, we we actually see hello message displayed. Like that's really cool. So yeah, we actually managed to compile the language into assembly. So that's really nice. Now for the second part, I wanted to implement the copy method. And yeah, like as for the string output, we also have the implementation in MIPS, SPIM, whatever it's called. And yeah, I wanted to try and actually reuse it, something like that. So yeah, basically my idea for this one, I mean, it's just gonna be similar to copy pasting, but we need two extra variables that are gonna be global in the assembly code. It's gonna be the heap current position and the heap end position. So that way we know when to allocate memory. So it's pretty interesting. We are gonna implement the memory allocator again, but in assembly. So although it's gonna be much simpler, like we are not gonna worry about freeing and stuff. It's just gonna be allocating. So how copy works is well, when we start the program, we just set the heap start and heap end on the same address with the sysbreak. But after we call to copy, like we try to copy an object, we are gonna check if the size of the object would like overflow the current heap position if it goes above the limit. And if it does, then we have to allocate more memory with the sysbreak syscall. So yeah, basically the idea is we allocate 64K. I saw that's what they used in the assembly file, so I said, well, I'm just gonna use 64K as well. Why not? And after we allocate that memory, we can actually copy the object byte by byte. So we are going to have a for loop that copies from the prototype object into the current position in the heap. So we copy the object. So yeah, here I was copying from my last assembly project where I used the sysbreak to allocate memory for the tape for brainfuck. And yeah, basically that was the same idea there. And the only difference is that for brainfuck you only do one allocation because you are limited to 30,000 bytes or something. I don't remember exactly, but yeah. So I created these two variables, heap start and heap end. I'll end up renaming them, I guess, heap position and heap end or something, if I remember correctly. And yeah, they'll just mean heap end will be our current like limit for the memory address, and heap position will be the current position in the heap. So yeah, we don't really keep track of the start, so I mean it is what it is. But yeah, like as a cool trick, if you call to the break syscall with argument of 0, you get back the current position. So I mean it's just like it doesn't do anything, so it obviously it returns the old position. So for the copy syscall, I actually saved the self variable, yeah. Then we need the self size because that's what we are gonna copy, and we need to multiply it by 8 because it's in keywords. The size is in keywords, so we have to shift left by 3, and that means multiply by 8. Right, so that's another way to do it. So now the next thing would be to do the compare, and for the compare we can use j less equal and then use a label. And yeah, basically we are gonna just add to RBX the current heap position. We are gonna compare that to heap end, and if it's less than equal we jump to OK, otherwise we have to allocate some memory. So again we are gonna use sysbreak. We are gonna put 64k in RDI so that we allocate 64k, and then we just have to do syscall. We don't even need to call to system like sbreak again because it's gonna return in arrax. It's gonna return the new limit. So yeah, it's not really needed to call it twice. But whatever. I think I'll remove it. And then if it's I guess if it's okay, we have to restore the current object and get its size again probably because yeah. And then we are gonna have a loop. It's gonna be like a for loop but in assembly obviously. And what this loop is gonna do is take one byte from the prototype object, so from a. I guess it's not really the prototype object, it's prototype only if you instantiate it, like we're gonna do for main. But when it's gonna be like random object that copy, it's gonna be still some place from memory. So yeah, but I mean still doesn't really matter. But yeah, here now we need to copy the from self. We need to copy the current block of 8 bytes, like a single word. And I guess we would have to increment the source and decrement the counter. So that's like, hmm, yeah, we should increment the arrayx by 8. I don't know if inc works, so I'm just gonna use add, and then we can decrement rbx because that's our counter. And yeah, after that we have to move into the heap position the rbx value. But I think this is not really correct because we have to also keep in mind that we are in a loop, so we have to actually initialize correctly RDI there, yeah, like using heap position. and we need to use mov because we put on the stack we put the value, so we can use mov. And I think that's everything probably. Yeah, like just put the current chunk into RDI, copy the slot. I have no idea why I changed it multiple times because that was right. Anyway, and after that we have to increment the current position of the heap by 8, like a word. Then we compare RBX to 0, and if it's greater than 0, we jump back to the loop label. So we go again and copy another byte from the original place. And at the end, we just have to make sure that we pop the values in the right order. I mean, yeah, I guess they'll be in the right order. So we just pop RAX, which is gonna be the new object, the new self, basically, and we just return it. I mean, I guess not specifically the new self, but it's the return type of the function, of the method. And yeah, here I was getting a segmentation fault. I guess the segmentation fault was because I haven't implemented init yet, so but it's still a good thing that I went step by step through the compiler. And yeah, I mean, copy, I think it worked first time. Yeah, I think it did actually. I think it worked first try. Let's see. I mean, I deleted that thing from there, like this sbreak call. But yeah, actually it worked first try, so that's pretty nice. And yeah, the missing thing was we don't implement yet init or any other function, so obviously it's gonna fail. But I'm gonna do just the bare minimum to make it not fail. So that's what I'm gonna do after this small debugging session. So yeah, let's see. And yeah, as I said, I just went ahead and put the bare minimum in it. Basically, we just have to push RBP, save RX. I guess we just have to use ret. That's the bare minimum. But I mean, I just wanted to have more stuff prepared, basically. But yeah, I mean, this is the bare minimum for the function calls to work. And yeah, we'll still have to implement the actual implementation, obviously. And now the last thing I had to do was to also go to the last, because now it failed on main.main. So also need to add a bare minimum for function calls. So for the other thing. So yeah, and after that everything was basically done. And see now the executable doesn't crash anymore. So everything seems to be working okay-ish. We still have to implement all the actual source code, but yeah, I just made this really small example, and let's try to use this one to get get it running and get it to show hello world. Like that's the first step that we want to do. Implement the minimum set of assembly that makes that show hello world. So yeah, let's see how that will go. Okay, and continuing with the assembly, I wanted to implement the init generation. And for this one, I wanted to take, let's say, an example like object.init or any other like that, and try to implement it myself in Phasm. And I guess the idea was to just copy paste one of the examples from there and try to come up with a method of keeping all the registers the same value at the end as they were in the beginning. And yeah, that was the idea. So how I did it was to first we are gonna use EAX as usual as the register that holds self, Well, at least that's what it does in the input and output of the function. But while we are inside of the function, we can do whatever we want with it. We can save it on the stack and then use it for operations. And how are we gonna do that is we are gonna use ABX as the, let's say, place where we are gonna store uh, the value of EAX while we execute the function. So we are gonna push the value of RBX on the stack, and at the end we are gonna pop it, and that way we are also gonna keep what the value was inside of RBX. So after we push the value of RBX on the stack, we are free to just move EX into RBX. So yeah, and that's what I was about to do here. Just initialize EBX with, or I guess RBX with RAX, I mean the 64-bit registers. And after that we can actually use RAX to do whatever we want. And for this xinit example, what we need to do is to call to the parent init. And why do we need to save rux is because this parent will actually change its value, right? So the value of rux is going to change, and also the value of rbx is I mean the value of rbx is not going to change because also the parent is going to use push and pop for rbx, so it's going to be like the same value. And now I just wanted to see an example where we actually set some stuff in the variables. So for example, this a here has some initialization for some of its arguments. And I guess the logic of how to do it is to probably just get the position of the argument and store into, so we get the constant into array x, and then we should be able to store the value into, I guess, rbx, because rbx is going to contain the pointer to self, right? So that's what I'm thinking, but I'm not sure if you can store the value like that, like do like I know you can do memory offset when you read from memory, but I don't know if you can write to a memory offset. So that's something we're gonna figure it out, because yeah, that's gonna happen at some point. But now I was just copy pasting from the assembly file into the C file, so just taking what I manually done and using printfs to create that blueprint. And we still have that to do there to create the attributes expression. And something really cool happened, like when I was also changing the methods, and actually we are gonna be left with only one place where we are gonna generate expressions, and that's gonna be the same thing for both the initialization expressions and for the bodies, because they are both expressions. So it's gonna be a single place where we actually have to generate the expressions, and I think that's pretty nice, because yeah, I mean, like, it would have been two function calls, so it is still the same thing, but I mean, it I don't know, it just came out really clean for some reason. Hopefully it's not a bad sign, because usually that's how it goes. When something works really well first try, it's yeah, from my experience at least, that's what happens. So yeah, basically I created this function that's gonna iterate over the attributes of a class, and it has to initialize the attributes with expressions. So I just move the to do in yeah, like we always do that, create wrappers for wrappers, and that's funny. But I mean, this one actually made sense. So yeah, we create a for loop over all the attributes, and now we need another function that is gonna generate the assembly for one single attribute. So we try to make it, I don't know, like a bottom up or something. Yeah, bottom up parser, or I guess code generator. It's gonna generate the code only for the smallest thing possible, so something like that. And yeah, basically this emit object init attribute is gonna take in the index of the class that it's a part of, the index of the attribute, and the context basically. So yeah, and here at this point I went ahead and imported the uh, TAC library, which we did. I don't remember exactly when, but it was like, I mean, from the title you would guess which video it was, but yeah. And the point of this tree address code is we are gonna convert each expression into really simple expressions that I guess they can be probably easily converted from expression to assembly. At least that's how it feels like. At least, yeah, like with FASM you can have pretty weird syntax, and maybe it's gonna be easier than simple assembly. But yeah, to be honest, I don't know. Like, my fear is that in the three others code representation, we have like limitless variables. We have T0, T1, Tn. Basically, we can have like 20 variables, but we only have a limited number of registers. So that's something I'm not really sure how we are gonna tackle that, because like if you can have variables, that would be stupid to have variables in assembly. But if we can have variables, then it would be extremely easy. But yeah, and yeah, now on the like what I was doing was trying to do the same thing I did for init, but for functions. And the only difference between like what I found is that when we do functions, we no longer restore the self into Rux. We only restore self into Rux when it's an init. So basically, that's the only difference. And I think obviously it makes sense because the init function, like the constructor of a class, should return self, obviously. But like a simple method doesn't really have the same requirement. It can return basically anything, so it doesn't need to, have that thing there. So I think that's pretty neat. Like being able to make everything almost like look really similar. It's really good for this kind of compiler because it's gonna make it really easy to make it really generic. Like yeah, because it's not gonna happen that we are gonna leak some values in some registers and we are not gonna know where that comes from. We are gonna try to keep everything like a function call doesn't change anything except, I guess, EAX. So, but yeah, I mean, I also have some functions where I change RDI and RSI, but those are usually used in like, to be honest, I have no idea what people like assembly people use them for. Usually I use them for copying from a string to another string, like from bytes to another bytes. Yeah, just the way I do it. So here I actually created that function that I told you about, the assembler emit expression, and this one is going to be called both in the for the function like method body and for the attribute initialization. So here we call it, and there for the method init we also do that. The only thing I had to do extra for method was to get the container class for the method because we need reference to self. That's the point of this J variable. And yeah, now we have the assembler emit expression that takes in an expression, and it has to generate the assembly for that expression. And like we really got to this point where it's really modular. We get an expression and we want to generate the assembly for that expression. So it's really nice. Yeah, and here I also changed the object copy and the IO print string or out string, whatever, because I wanted to make it look similar to our other functions. So for example, instead of using RBX for everything like calculations, I used arrayx and I stored like we do for the other stuff. I stored in RBX. I stored the value of arrayx. So yeah, now we actually follow a bit better the convention that we are gonna use for the other methods. And yeah, here look, as I told you, I'm like usually I'm using RDI and RSI as pointers in arrays. I have no idea. Like that's what I remember I learned about at some point, and that's how I use them. Yeah, I mean whatever. So yeah, but we have to keep in mind that those values are gonna be always random. Like we don't rely on them for anything. They'd be like auxiliary stuff. But RBX and RAX kind of need to be. We need to be a bit careful about them. So at least RAX will always refer to self. Yeah, will kind of yeah always refer to self, and RBX will always be the copy to self. So yeah, and I guess here I was just trying to see how the generated code looks like, and not sure. I mean, just made a checkpoint, I guess, and just because I wanted to start to work on the three others code to assembly generation. So here I made a for loop over all the instructions because, as you know, the node is a tree, like the expression is a tree, like the AST, but the tree address code is a list of instructions, and they are assembly like instructions. So that's why I'm saying it's going to be a bit easier to take a single instruction and convert it to assembly. So that's exactly what I have there. I have like a function called assembler emit tag instruction, and that's like a single instruction written in tree address code that we need to convert to a single instruction. I guess can be more instructions, but we need to convert a tree address code instruction to assembly instructions. So I think this should be easy enough, probably. Like we are at a really close point of ending the compiler, finishing it. Because yeah, I mean, we got to the point where we have a tree address code instruction. We have the entire context available in that function, and we want to generate some assembly code. So I think we are pretty close. I mean, obviously we cannot really finish it in 1 or 2 days because, but maybe we can because even though there are a lot of instructions, I think that once you get a hang of 1 or 2 of them, it should become really easy to do the rest. Like probably the hardest part is gonna be doing the function calls, and as I said, I'm not really sure how difficult it's gonna be to handle the infinite number of variables, and we are restricted to only a couple of registers. So there must be like an algorithm that exists to convert tree address code variables, like an amount of infinite variables, to registers. But I have no idea what that is. So yeah, But here I implemented the tree address code generation for a simple integer, and the idea was to just take the value that we get in the tree address code, because how it's gonna be generated is gonna be a variable is gonna be equal to an int, and then we return the variable. So we have to generate both the identifier and the int. And yeah, the int, how it works, that function, is we need to generate a new constant variable, or like yeah, like a new constant uh, for uh, for our assembler. And here is the part where I said that FASM has a pretty weird syntax, because I was able to just say t1 or like t0 is equal to the address of the constant, and it worked. Like, you can define these kind of constant variables where you don't really need to have you can have like t0 is equal to 1, and after that when you use again t0, it has like it's like the C preprocessor when you do define, so that's what it reminds me of. But yeah, here I tried it and it actually worked for some reason, like pretty weird. And then I just did move that T0 into ArrayX, and yeah, it actually worked. So here I started out assembly, GDB, sorry, and I went through the instructions. And here, when we go through the instructions from the main file, we should be able to see that we get a 0 in array x at the end, because that's what we have in the main function. We have return 0. So here, when I look at the values in array x, we can see that it's an int because it's a 3, it has a size of 4, and there was all zeros. And here I said, okay, let's try another value. Let's try 69. And again, here I try to look at array x, and when we look at what value we have there, it's actually 69. So we actually managed to get it to return you know return integers, so that's pretty nice. But now I wanted to go ahead and do the same thing for methods, like be able to call a method, you know. This one, and yeah, I guess to be able to print hello world, we actually also need the tag instruction for strings, but it's the same as for int. We just need to create those extra constants. And the only issue I had here was that new lines or stuff is not escaped, right? So we have to do the escaping ourselves. Like, we might do something like, if we find alphanumeric characters, we keep them. But if we find anything weird, we show the hex code or something. Not really sure yet how it's gonna be, but probably something like that. So yeah, I just removed the new line because I'm not gonna do that right now. And now we have, I guess we have the string constant. So at least we have that. But we don't have yet the function call, so that's what I need to do. And first I wanted to remind myself again how the function call looks like. So I just copy pasted the code from the print functionality. And yeah, I wanted just to see how the method call looks like. And I guess what I did was to push all the, let's call them arguments on the stack, then call to the method, and then pop all the arguments from the stack. And yeah, I guess there was only one argument, but if we have multiple arguments, we want to push them in the reverse order. So that's the idea. But here, yeah, it's gonna be pretty strange how are we gonna be able to implement the method calls. But for now, I'm just gonna hard code the method call to IO print string, so we can actually do hello world. But in the future, I'm gonna, actually do the right method. But yeah, here I inserted the arguments in the reverse order, and then I popped all the arguments. To be honest, I'm not sure if you can pop without an argument, so if you can pop without RAX, but I just did, you know, doesn't really matter. And here I was trying to use that FASM syntax for using constants, but it's not gonna work. It only works for immediate values and addresses, so it's not really gonna work. But yeah, here I just said, okay, then how about me trying to use just the IO outstring function. So instead of doing the generic function, I just did IO outstring and just leave it like that. So now if we compile everything, we are gonna see, uh, well, yeah, I have that t1 variable undefined, but I'm just gonna remove it. And there we do push t0, which is our first argument. It's string constant 12 or whatever. And then we do call to IO outstring. So I just hard coded everything to make it work. And now if we do, yeah, now if we run our code, we actually get a hello world message. So that's pretty nice. So we went from hard coding it into assembly to actually making it work from the C code, and I guess that's pretty good result for today. So yeah, for the third part, I guess pretty good result. Okay, so for the next part, what I wanted to do was to actually fix some of the to-dos that I left here. So one that's really important in my opinion is to make the function calls work properly. And that is because it's like using function call, at least to printf, is the easiest way to debug our code. So yeah, yeah, in my opinion, I think that dispatch call should be done first. At least I'll make it work for printing strings. But yeah, I think it's really important to have it because that way we can easily test, let's say, if statements, while statements, stuff like that, prints. Because at this point we can print both numbers and strings, so we can do math operations and check that everything works. And after we manage to do function calls, let's work a bit on ifs, while loops, the more interesting stuff, and we'll leave all the math operations for the final part. So yeah, I think that should do the job. So here I found something interesting about I guess register convention. So it's like RAX, RCX, RDX, RDI, RSI, and some else are color saved. So basically that means that the caller must save the registers, otherwise they might get destroyed. And RBX, RBP, and RSP are callee saved, so you can assume that the callee saved will be left as they are. So that's why we have to do that push RBP and pop RBP. It's more because of the convention. So yeah, we are gonna use RBP, as the convention shows. And then for RAX, obviously it's gonna be destroyed on function calls because it's the return value. And I guess RDI, all of those are mainly, usually they are used as arguments, so I'm not surprised, to be honest. And yeah, RBP and RSP are the return pointer and the stack pointer, so obviously they won't be destroyed. They should come out like with the same values as they went in, basically. So yeah, we have to keep that in mind when we do function calls. And yeah, here what I thought is I no longer want to use those labels from Phasm for constant values. And how about we actually allocate memory on the stack and use the stack for local variables? I mean, as it should be used, you know. So I added this dynamic array of characters on in the tag expression, in the tag expression result. Right now I think I made it an int, but in the end it's gonna be a char pointer array because we kind of need to know the position of each variable, like local variable that we declare, because like we can get the position from the name, like split the name and get the integer value like its index, but that's really ugly. So I thought, why not just keep them all in a list, keep all these local variables in a list, and yeah, basically just do that. So yeah, here, yeah, I mean this doesn't isn't really important. I was just thinking maybe I can use something else instead of char pointer, but it's not really a great idea. I mean I have to modify quite a lot of stuff. So yeah, I guess like if I started out with this, like the implementation, maybe it would have been nicer. But you know, like just using the dynamic array also works fine. So yeah, that's good. So yeah, here I actually changed the result to be the new structure that I made, the tag result. And yeah, basically instead of just doing the dynamic array straight up, like just doing a dynamic array, I'm gonna use a wrapper structure for the dynamic array because it's gonna contain, like I guess, all the instructions and also the locals. And yeah, it's easier to just use the context for the locals and then copy the array once it is done, like the function completes. So I guess now with locals, like an array of locals, we can actually allocate some memory on the stack for them, and we should be able to use the names as indices in the array and figure out which place on the stack belongs to which local variable, right? So that's how we can do it. And yeah, we can also have a function for that. It's like this part. Yeah, I have to remember exactly, but I mean, yeah, we can use you know, like a separate function that gets in a local name, like those t0, t1, and so on and so forth, and gives us back the index on the stack. The only thing that I think it's maybe might require a bit of a change in the future is also putting the variables that come from like the parameters somehow in these local variables. Like in some way we first initialize all the temporary variables with the arguments and then we use those variables instead of the arguments. Maybe something like that. But yeah, we'll have to see. Because if we have functions with arguments, then the arguments will also be on the stack, and yeah, we will be a bit. It's gonna be a bit weird when we try to access like the difference between, like making a difference between, you know, local arguments from the tag expression and like function parameters. That's gonna be a bit strange to figure out how to do. And I think that if we just put all the arguments of the function into temporary variables the first time we enter the function body or something. I don't know. Maybe that's gonna work better. But yeah, like that's not really ideal though. because we also want to be able to access like the attributes, and yeah, that's not really ideal. So we'll have to see. Maybe it's gonna be like the assembly for getting an attribute or a function argument are gonna be a bit different. They are not gonna be the exact same as loading a temporary variable. So yeah, that's we'll have to see, because I guess we can differentiate between local variables and attributes slash function arguments, because the local variables, all of them are gonna be in that locals array, but the attributes and function arguments are not gonna be in that array. So that makes sense. So I guess here I was trying to see how people actually use the stack, right? So basically we have the RSP pointer, which is the bottom of the. To be honest, I don't even know how to explain the concept because it's weird. I like to do like hand gestures when I think about it, because you have the stack pointer, which is, let's say, at RSP, and then when you decrease, let's say, 1 byte, it moves up. But when you actually write to it, you write from top to bottom. So the okay, let's say we decrease 8 from we decrement 8 from the RSP. So we allocated 8 bytes, but the first byte is the one on the top. So somehow the stack grows from bottom to top, like from down to up. But when you write to it, you obviously have to write to the lower address, right? So yeah, that's why it's a bit strange, maybe. Like that's why it's like I find it really confusing. So, or at least that's how I felt when I first tried to use it, because yeah, it's like completely new. Usually, when you work with a heap, like or any other type of memory, you increase the size. Like obviously, you increase the size by 8. Then you take the first pointer, like the original pointer, and you can write to it 8 bytes. But the stack is a bit reversed, in the sense that you to increase the capacity you decrease by 8, and now you have to take the first pointer, which is no longer the one that you decrease from. It's the pointer minus 8, the one that you now have, and you can only write 8 bytes, right? So that's the it's like using the reverse heap. Yeah, I mean, yeah, once you do a lot of I guess exercises with a stack, you kind of get used to it. So, and especially if you try to just use push and pop, that makes it really easy. Like you don't even have to think about it. But once you need local variables, you cannot really. I mean, you can do push a lot of times, but like do a lot of pushes and pops. But yeah, at some point you are still gonna need to access, like do random access in the stack. So yeah, I mean it's better to just get used to it. So yeah, but I guess here at this point I was just doing the int and string and probably the boolean also, because I mean I did these ones already, but now just change from whatever I was using to using the stack, because it's better. And as you can see, we allocate like number of locals by decreasing 8 times the number of locals, and then we can store stuff. Here there was a small problem because I was printing the comment, and yeah, I maybe I'll try to do like a string wrapper like in Python to have better printing for the comments. But I mean that's something extra. I don't know. And yeah, basically we can now store our t variables on the stack. So the only extra thing that we need to worry about is how we are going to handle the parameters to the functions, and maybe the attributes. So those are the last things. Probably we'll have like an if statement. If it is local variable, then do whatever you do for locals. If it is anything else, try to search for that variable in the context somehow. And if it's an attribute, I think it's pretty easy to take the attribute though, because you need the self. Like we need to get uh, RBX because that contains self, and then we need to go to the prototype object and take the value from there. So yeah, it's not crazy difficult. And then for the function arguments, it's still on the stack, but we'll have to see how we are gonna reference it because yeah, now RBP has moved, but I think RSP is still on the original position. So well, I guess not really, because RSP moves when you allocate memory, and RBP stays in the original position. So yeah, actually we'll be able to take the arguments by doing RBP plus. Like RBP plus 16 is going to be the first argument, RBP plus 24 the second one, and so on. Yeah, yeah. I guess it's not impossible to do so. Okay, and now for the function call, the idea is well, if we have self, if we do a function call on self, then yeah, we have to pop RBX, like move RBX into RAX because we need self, right? And if we do, I guess, a function call on something else, we already have uh, racks with the right value, so I don't think we need to worry about that much. Or yeah, like we have to load the racks from the stack. But if it's self, we need to load the racks from RBX. So I think that's how it works. And yeah, so that's like the edge case. If we find the self, like a self dispatch, then we use RBX as the self. And if we find another type of dispatch, like a function call on some value, we use that value as the self. And then to get the function, basically, I mean the method name, we already have it, but getting the actual class is might be a bit difficult because if we get the current class, in our case it's gonna be main, you know, and yeah, that I guess doesn't work. But here the edge case is, I guess we have to go. I guess it's not really an edge case, but we need to iterate through the implementation mapping of all the methods and search for our method, right? And we need to find the implementation that is on our current class for our current method. And then we actually need to use the parent, like the parent class, or like the last class that defined that method, which is also in the implementation mapping. So on this one, I really thought ahead, right? Um, so after that one, a pretty small bug that kept bugging me was being able to move the registers back into memory. And like by looking at the object dump of main of like our source code, I saw that GDB generates somehow those keywords pointer. And I thought, okay, let me try to use that also, but it actually I should have used only keyword for that. Like you have to use just keyword and everything should work, right? So I just decided to put like everywhere where I do memory addressing, I put keyword because I mean let's just put keyword everywhere, why not? And yeah, that actually fixed the issue. And now we, as you can see, we see both the one and the hello world from the print. So it's really cool. And yeah, it also scares, and I think that's really cool. So we can have now we can actually print stuff. So that's really nice, and we can use those print statements for different kind of, I guess, checks, right? Like we can check that the if works by doing different prints. Like we can print one message on the if on the then branch and another message on the else branch. So yeah. So to make the conditional branching work, like the if statements and the while loops, we need to implement, I think, three things. The emit label function, which will just display the label. And here I spent a bit of more time because I wasn't really sure if the label is going to be global or not. But what I learned was that if the label starts with a dot, then it's going to be considered local, and it's going to be like local inside of the current global label. So if we have a function and yeah, in that function we have a label that starts with dot, then the label will be local. So everything is good because um, at the level of an expression, the labels are gonna be all different, I guess. So that's good, right? But on the level of the program, the labels are gonna be like the same. So yeah, inside of the body of a function, we are gonna have different labels, but maybe they will repeat in the entire class or in the entire program. So that's one thing. And yeah, I don't know why I didn't search directly if it's possible to have local labels. I almost went ahead and tried to implement some logic for it, but I mean, if it works, it works, you know. We don't have to change anything. So all we have to do is to print the label, and then the next thing that we need for making the ifs work is the jump condition. Or like we have both unconditional jump and jump if true. So the unconditional jump is just jump, like jump and the name of the label. Then on the conditional jump, it becomes a bit more interesting because um, for conditional jump, we need to access the boolean value inside of the boolean object. So yeah, we can use jump not zero, and jump not zero basically is used with test. So we test rux, and if that thing is not zero, then it means that we should not jump, right? Jump if not zero. Yeah. So if it's true, it jumps. Okay. And yeah, here I just took the value from the stack and put it into rux. But one extra thing we have to do is to actually access the boolean slot. So yeah, here of course it did a segmentation fault. I don't remember exactly why, but um, probably I guess I forgot to implement some of the instruction that are required for the ifs. I guess that's what happened because I saw that in here in this function for some reason it jumps to some random function call. So I thought, okay, it's the fifth one, so we need to do a sign value because it was, I don't know, it was doing some random stuff. And yeah, we actually have to implement also a sign value because that's what's gonna be used for the branches, right? Like if we get on the then branch, we need to get the value of the then branch, and otherwise we need to get the value of the else branch. So that's why we need a sign value to store that the results from there. And Yeah, basically that one is just moving from memory to another memory, but I don't think we can do memory to memory. I think we need to do memory to register and then register to memory. I haven't even checked, but I'm pretty sure you cannot do memory to memory because then what's the point of registers, right? So after that, we actually managed to get the ifs working. So yeah, I guess it was just that simple. And I thought, how about trying to test the while loops? Or I guess it didn't really work, right? Because yeah, then I would be stuck at here. So yeah, as I said, we need to access the value of the boolean. So we actually need to index into the tag. And I'm not sure if I should use the that bool slot there. It feels a bit wrong because it's like it's defined globally, but it's not defined by me in this code. It's defined in the assembly of the prelude, so it's a bit weird to use it. Yeah, but I mean, maybe I should define like a variable for it in the code, and then it would be more fine. But yeah, like hard coding it like that feels a bit wrong. But yeah, here I was just debugging that everything works fine, and I realized that I forgot to set, I guess, the value of a boolean to be keyword, and it was only a byte. And yeah, it was pretty weird because I was using db, and I saw that because the memory wasn't or zero, it was like some garbage there in the place of the boolean slot. So I just went ahead and changed it to DQ, and now it works, right? So that was the only change that we needed, well, other than the accessing of the Boolean slot itself, but yeah, it was working. So here I thought, okay, let's try to call to a function, but for some reason it's segmentation faulting, so I guess we are still not quite right on that. But I mean, it's still okay. I don't know. And here I try to do the while loop, right? Because I mean, it is a while loop, conditional, right? And yeah, I mean, I guess the while loop works at some extent, but to actually have it work, we need to implement the assign not operator because when we do the while loops, I didn't want to implement another jump if statement, and I wanted to reuse branch true. So the while loop, if you've seen the tag part, it works by jumping back to the loop label, and if the loop condition is not true, then it jumps out, right? So that's why we need to negate the predicate. So either I was using jump if not true, or negate the predicate. So to negate the predicate, I thought it might be interesting to try to use object copy to copy the current boolean and create a new one, right? So I think the idea is that when you do something on an expression, you actually have to generate new objects anyway. So I guess that actually makes sense. But yeah, so I think we need to use object.copy when we do not expression. And I mean, the not expression will be required anyway. So that's why I think it's better to use not if basically. And yeah, to flip the boolean, I think we can do XOR on the memory address. I think that should work. And yeah, here I thought that it didn't work for some reason, so I went into doing the GDB, but I think it was actually fine. I guess I just forgot to actually call the executable to see the results. And yeah, here I was just looking at how the like calls work, and I saw that well, it was just it was an infinite loop. So I thought that Well, what happens if I just run the executable? And yeah, it actually seems to work, although we get some segmentation faults. Again, probably we do something wrong somewhere, but we'll need to figure that out in the next part. So yeah, we'll have to see. Okay, and in this part, I wanted to implement some more triadic code instructions. And yeah, because yesterday we did like more on the prelude assembly, so on the actual code itself. But now we need to extend our like compiler capabilities. We need to add the possibility to compile, comparisons, I guess. So like maybe less than and less than equal. Those would be easier because I started with equal, but I realized that equal is gonna be a bit more tricky because you can actually compare any objects, any two objects. I mean, as long as they have the same type, if I remember correctly, but still you can compare any type of object because it compares, I guess, the memory location. So we might have to implement the mem compare for that, and yeah, that would be interesting on its own, I guess. So for this one, I thought, well, let's try to do just a simple comparisons. And here I was looking for how we can use the CMP instruction because compare doesn't really set any registers with values. It kind of does this thing where it sets the flags of the like the flag register. And there I have no idea why the FASM website was not working. I guess it was down for some reason. Although I mean, it doesn't make any sense, but I mean, it is what it is. Or I guess it was what it was. And here at this point, yeah, I actually figured out that we have to use that CF flag when it's the compare doesn't work, but I still couldn't get any good answer. So like on how to actually get it, right? So what I did was to just write down a function where I did a comparison, and I looked at the assembly, how it looks like. And yeah, it actually found that S that set L instruction, and set L checks if the CF flag is set or something like that. It checks if the comparison was like smaller than, and if you do uh, set LE, it is for doing less than equal. So that's also what I found in the generated assembly code when I looked at my like C code generated, and yeah, also that move zx, which extends with 0 apparently. Like if you move something smaller into something bigger, it puts zeros in the beginning. So yeah, uh, but yeah, that was actually a really good find, set less than equal, because now the less than like the less than instruction is gonna be just copy paste, but it will use set L, so no longer equal, right? So yeah, here I guess I had a small bug because I put the operands in the like other way around or something like that. Although it was more like, I guess I renamed some stuff incorrectly, and I was doing a compare against itself or something like that. It was like uh, T1 is more or than T1, and obviously that's always true. And yeah, I mean, in the end I figured that out. But here again, like to use the result, we need to create a new Boolean object. So that's what I meant by it's a bit problematic with my instruction set, because even though it's really simplistic, we still have to create these wrapper objects for values. And yeah, I don't know, it felt really annoying to do that. Like, yeah, I'm not sure how I felt about it because you have to create the object, then you have to take the address to its field and set the value. And I don't know if I'm doing it wrong or something, but it feels really like meh to do it. Like it's ugly. I don't know. I thought that it might be a bit nicer when you do it, but it actually was not. And yeah, here I realized that to be able to set that value, we actually need three registers to do that, or like three places in memory to hold our values, because the first one is going to be the pointer to the start of the boolean object. The second one needs to be the pointer to its field, and the third one is going to be the the result. And we need two registers at least, because we cannot move from memory to memory. We need to move from memory to register and then from register to memory. So if we need three slots, um, then two of them have to be registers. Yeah, I don't think it works with only one register there. Yeah, because the second one, like the second move is gonna be a move to an address. So yeah, you cannot really do that with only one register. So yeah, we needed two. So here I think I saw that issue where I had the the same result every time. So I tried to debug it, but I mean the code was pretty wrong in the equal comparison. So I thought, why not just create this get variable function that will load a variable from the memory, and I don't really have to worry about how that looks like. I just give it the name of the variable, like it's gonna be t0, t1, or an attribute name, for example, and it's gonna give me back the. I guess it's not gonna give me back anything. It's just gonna generate the instruction that loads that memory into array X. So that's my idea. And then after you call this function, you know that you can use array X as that variable basically. And I also did the opposite of it, that stores on in the memory. You give it, like, again, the variable name and I guess the value, and it's gonna store it. And by value I mean like the pointer to the object, something like that, right? So yeah, and then I added the to do comments because I want the assembler to fail, or like, yeah, I want Phasm to fail if we actually need to implement something more, right? So yeah, and here at this point I just went ahead and replaced everywhere in the code the like the old method of doing it by calculating the offset, and then I mean it's the same thing basically, but instead of having that code spread out everywhere, I just use this emit load variable, and I'll do the same thing for I guess saving the variables. And here I also thought about doing this as a separate function to be able to load the, let's say, the inner value of an object, but I don't know how I feel about it. It's I mean, it sounds useful, but yeah, I mean, I guess this is what I'm gonna try to do, have these functions that do a really small thing, and then have my larger uh, have my bigger functions that represent the tree address code instruction look more like the tree address code instruction itself, right? So that's what I'm thinking. And maybe, I guess, my other problem with the tree address code was that maybe the instructions should only use like two variables at once, like at the most, because sometimes I use three variables and that, I mean, it still works. I can use RDI and RSI as extra registers because they are always gonna change, so that doesn't matter. But I still have to keep RBX the same, so that's the only restriction I have. But yeah, at this point I was just, you know, removing the old code and replacing it with a new method of doing it. And yeah, as I said, the less than equal instruction, I just copy pasted the function for less than equal and just change that s set LE into set L. And that was the only change. So maybe there's something that I can do there to not have that duplicate, but I mean, it's still nice that it was only one character to implement that function. And yeah, now we also have comparisons in our assembly code, and I guess the function calls and such, all the if statements and while loops. So yeah, I think this is a pretty good point right now. So yeah, that's this is really good.